Okay, so let's continue with Ampere's law. Specifically, we're going to start looking at solenoids and toroids. First, let's look at a solenoid. Before we get into that, let's remind ourselves very briefly what Ampere's law says. And so let's see. We have the magnetic field along a closed loop is directly proportional to the current within that loop, right? Which should, remind us very closely of Gauss's law. I guess we can. Which said the electric field through a surface, right, as opposed to the magnetic field along a closed loop, is directly proportional to the, it's not how you spell charge, charge within that surface, right? And so these are the two relationships we have. Today we are going to focus on Ampere's law. Shouldn't be a huge surprise. And so we're going to start with a solenoid. Well, first of all, what is a solenoid? Great question. So that's just like a helical coil of wire, right? And in class on Wednesday, we can start class with a demo of how a solenoid works. I'll hook it up to a power supply and we'll pick some stuff up with magnetism. And then we'll see that when you remove the current, the magnetic field goes away and everything falls out. So we'll try to do that on Wednesday. Please remind me if I forget. Okay, and so, right, if we were to draw a solenoid, right, it might look something like this, where we can have a current that flows in one end and out the other. We are kind of running into the problem of drawing 3D things on a 2D surface, and we're kind of at the limitations of what we can really do with that. So what I'm going to do is kind of draw just the segments of wire that are coming like out of the board, right? And you're going to imagine the wire coils through, it goes all the way around, but just so we're not super messy, it's going to be pretty messy either way. We're going to draw it this way, right? And so you could imagine that this connects through, goes to here, this comes up, and it loops into there, and so on and so forth. Dashed line was a crazy choice for this. Oh, and that's how many back you can go. That's cool. Right. And so we're going to continue like this, and then we're going to draw, quick reminder, this is out of page, and this is into page. All right, and you remember if an arrow's flying at you, you just see the tip. If it's flying away from you, you see the feathers in the back. All right, and so what we're gonna do is we're gonna have the current come out of the page at the top and go into the page at the bottom. And so I'm gonna pick a slightly different color for just, visibility. Sure. Well, we'll do red. And so out of the page up here, into the page down here. and that's going to be true all throughout our coil. Okay, and so we had discussed that if we have a current carrying wire, in general, the magnetic field is going to go around like this. Right, and so it curves around, and that's going to be true, all along this wire, right? It's a long wire. We don't have to worry about edge effects. But the magnetic field's always going to be curling around our wire. And so, well, if we were to imagine our wire with current coming out of the page, right, we have our thumb point out of the page, and then let's see, so our fingers are curling this way up here, that way down there, here, 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 and we get the magnetic field's going to wrap around that way. Wow. Right, and so we're going to have a counterclockwise magnetic field if the current's coming out of the page, and conversely, if the current's going into the page, now our thumb points into the board. All right, make sure you're using your right hand, and we get the magnetic field goes something like this. Right, curls around clockwise. All right, so those are going to be the two things we keep in mind here as we go through and draw this magnetic field. And so we're going to start with the components of the wire at the top. And so up here we're going to have, right, the magnetic field kind of comes around like this. Right, we can go maybe a little further away. We still have some magnetic field. And as the further away you go, the more they're going to spread out, right? The closer they are, the stronger the field. The further away, the weaker the field, so they spread out more. And so we can do this all around on all of these wires. Okay, and then we can also kind of come along and do one more. And then we kind of have them running into each other. And so once we have them running into each other, it doesn't... Here, let me make a little bit more space. Dude, master of technology. Right, and so once they kind of start overlapping, we can just kind of do the net magnetic field, right? And it's going to follow like the same contours, but it's just a superposition of all the individual ones. And so, let's make sure these arrows are here. And so it's going to point in the same direction as we would expect, right? All of these up top are pointing to the left. And so up top, the magnetic field is going to the left. All of them over on this left-hand side are going down, so the magnetic field goes down. Inside our coil, all of the magnetic fields point to the right, so we still have that. And then we go up here. And we have a reasonable magnetic field for that part. And we can do the exact opposite directions for the lower coils. And so we're going to maybe have it going this way here, that way there, something like this, right? And then also note that it's going to the right inside the coil. And I'm going to skip the secondary loop just to save space, and then we'll just go to the combination of them all. And so we go up over here to the right inside the coil, we go down outside, and then we go to the left below the coil. And so you can see if you look at the magnetic field inside the coil for both the top wires and the lower wires, the net magnetic field goes to the right. And so, as we can imagine, if we were to keep extending these, right, we're going to kind of have a little swirly thing going through here. And then eventually when we get to the center, it's pretty much just going to be a constant uniform magnetic field. Right, once you're far enough away from these wires, it's no longer going to really care that it dips in here, especially if these are all very small wires and they're tightly packed, right? We drew this to be extremely exaggerated, but in reality, when you have one of these coils, the wires are all touching, and we got something like this. And so if you imagine trying to have like these little wiggly areas in here, eventually you just get a nice loop where you have a nice constant magnetic field inside. And then if you had all the same with down here, you get here, and then eventually we have a uniform magnetic field inside the solenoid. And so that's the picture of how the magnetic field behaves within a solenoid that we're going to kind of work with. Right, and if my drawing's not the greatest, you can look at figure 2917 from the textbook, but it does essentially the same thing. And then I think they go maybe one step further, and they say, okay, so we have all these wires coming out of the board and into the board, and if we wanted to look at their magnetic fields, you can kind of start looking at, you know, a couple of them, and you're going to get something like this. Then if you include more and more, you get a stronger and stronger magnetic field inside, but it stays kind of dilute outside. And so the same thing can be true for these. That has to go this way, and this way. And that if we kept doing this and going on, we would eventually end up with a very strong uniform magnetic field inside, and a very weak non-uniform field outside, right? And so the main idea to keep in mind is that the top and the bottom wires work together inside the coil, whereas they don't really do any interact outside the coil. And so you get strong uniform magnetic fields inside, weak diffuse non-uniform magnetic fields outside. And that's you know, true in specific situations, right? It has to be much longer than it is tall. You know, you have to make sure there's the same current in there. They have to be packed reasonably close enough. You know, there's a bunch of assumptions that go into us being able to say we have an ideal solenoid. Okay. And so we're going to kind of continue with the kind of toy picture of a solenoid that we have. And so again, we're just going to kind of, we're you know, this is a very detailed, pretty realistic picture. This is a little less detailed, a little less realistic, but still good, right? We got the same overall result. And so now we're going to go to a model it's a bit more cartoony, but equally valid. And so what we do is, instead of really dealing with individual wires, we treat the whole thing like one block. All along this block, we have current coming out of the board, and then all the wires down here will have current going into the board. Right, and so that's the current that's doing that. And so then what we're going to do is say, essentially, if you're outside the solenoid, there's no net magnetic field. It's super weak, super diffuse, and like pretty not super far away from the surface. It's a very accurate assumption to say there's no net magnetic field. Let's give ourselves a bit more space. Okay, and so then we're going to go ahead and say, right, all of our previous drawings were kind of, terrible line, leading to us just saying, inside the solenoid, you have a uniform magnetic field. All right. Outside, you have no magnetic field. And so then we're going to draw our Amperian path. We'll do this in pink. And so the path I'm going to draw is going to come down here, across here, up here, over here. Terrible. Fair enough. And we're going to integrate along the path going counterclockwise. Right? And we chose to do so specifically so that this leg right here, we have the path integral going in the same direction as the magnetic field. That's the only reason we chose to integrate counterclockwise. You could have just as easily chose this path, and then you'd want to go clockwise, right? And again, you would want to do that so that the magnetic field and the path integral are lined up. But, you know, neither here nor there. And so we're going to call this point A, this corner B, C, and D. We're going to say we have some length H for our Amperian loop. Okay. And then just a friendly reminder, B dot ds is equal to mu naught I enclosed. Right. And then just, you know, the ds means a path integral, right? We had a dA before, that meant area. Here we have ds, that just means path, right? We're going along some path. And then we also have dV, which is volume, but we don't use a whole lot of the dVs. Right. And so, right, in Gauss's law, when we had dA, we had to figure out the area of our Gaussian surface. Here we have a ds, and so we need to find the length of our Amperian loop. Right, just a little friendly reminder. And so what we can do with that is you're always free to break up a path. And so we can say the integral of B dot ds is equal to the integral from A to B of B dot ds plus the integral B to C of B dot ds. I was not really thinking about the space here, but we can scroll. Fantastic. C to D, B dot ds, plus, then I guess D to A of B dot ds. All right, and so we start at A, we end at A. That means we did a closed loop, and the circle, you know, is happy. All right, because that little circle in the integral symbol, it just means you're doing a closed surface, loop, volume, whatever. Okay. And so, well, if we just have some magnetic field B that's constant, well, we can pull that out from along A to B. All right, this might not be true everywhere. We're just looking at A to B right now. And so we can say A to B, B dot ds is equal to B from A to B of ds, right? And so, you know, same direction, we get rid of the dot product. It's constant. We pull it out of the integral. I'm combining those steps. And then, well, this just turns into the length of from A to B, which we define to be h. And so we have BH, right? And so that's what the first integral is going to turn out to be. Let's go ahead and number these just for clarity. Okay, so that was 1. Let's look at 2. The integral from B to C of B dot ds. Well, so that means we're taking this path right now, and we have the magnetic field going this way, and ds is going this way, and over here, B is 0. But nonetheless, we're perpendicular in a dot product, and so that goes to 0, right? If you have B dot ds and they're perpendicular, then the dot product is 0, so we can get rid of that. And we will just, I guess, label 1, 2, 3, 4. And so if that was true for 2, it's going to be true for 4. And so goes to 0. Goes to 0. And so let's just take a look at 3. And we have C, D, B dot DS. We said outside the loop, B is equal to 0. So B dot DS is equal to 0. And so this whole integral, all right, is just equal to B times H. Where H is the height we picked for our loop. Okay. And so now we need to find I enclosed. Okay. And so if we have some current I traveling through this wire, right, and then going back into here, well, then the total current I enclosed is going to be however many times that happens, right? And so if we define N is going to be number of loops per length, and then we can say the length of our Gaussian loop is H, and so we have the total number of loops is equal to N times H. Yeah. Okay. And so then I enclosed is going to be I times NH, right? And again, N is just the lowercase n, is the number of loops per length. And so in a problem, you know, maybe it says you have 1,000 loops of wire in a 5 centimeter solenoid. And so you have N, the total number of loops, and then you have L, or 5 centimeters, as the length. You can find what your lowercase n is, the number of loops per length, and then you can multiply that by the length of your Gaussian, or your Amperian loop, and you're good to go. Okay? And so if we're going to combine these two into Gauss's law, Ampere's law, I'm a liar, my bad, we get BH is equal to I NH, and we need to slap a mu naught in there. Right? And so let's see. H, right? H cancels because we kind of made it up, right? It was just, you know, part of a surface we drew that's not even really there. Or a loop, I guess, not quite a surface. And so we get the magnetic field due to a solenoid is B is equal to mu naught I times N. And so this is for an ideal solenoid. Okay, cool. And so now let's start taking a look at the toroid. And so let's see, a toroid is just a solenoid that's kind of wrapped along itself, right? If we, I guess we'll start drawing. You know, if we have we can be like 2, 2, 2, 2, 2. Right, that's a horrible drawing. So right, we had all of our currents coming out of the page and going back into the page. Right, if we took this shape and then just kept going in a circle, we'd have a toroid. And so that's kind of what we're about to do. Well, at this point I can just... And so let's see. I am not going to go as in detail as the drawing in the book, right? Figure 2920 B. But what we can do is, right, if we have, right, all of the into the pages, and then each one of those corresponds to an out of the page. Yeah. Right, keep that guy in there. Stop it. Right, and so, you know, in the textbook, I think they put a lot more. Right, we got one. Right, but notice each one has a corresponding pair because a wire has to come out in the page, right? We're not just arbitrarily drawing a number of things in here. And if we said the magnetic field is going to be constant and uniform within this, right, we would get magnetic fields doing this. This is really not the best drawing. But, you know, we're not too perfect. It's all right. And so there's our toroid. And for this, let's see what we're going to do. Our Amperian loop is just going to go along the magnetic field within our toroid, right? All the magnetic field exists within the toroid, so we're going to look at the magnetic field in the toroid. And so, you know, let's say we're looking at some distance r away. And so we can take a gander at our integral b dot ds. And you know, you can take your ds, and if you're more comfortable with a dl, that's fine. Those are kind of used interchangeably in a lot of cases. Right, and so we're going around a closed loop. The loop is a circle. Well, first of all, dot product, they're parallel. So we can make this the integral of just b ds. And then the magnetic field's a constant, so we can say this is equal to b times the surface integral ds. And so we get b times some length, and it's the length of a full circle of radius r. And so we have a 2 pi r, right? Because when we integrate ds, we get some s or some capital L for a length. And so we just need to figure out how long that is, just like when we would have our E dot dA, right? We would get EA, and we would just plug in the area of interest. Here we get a BS, and that's no bullshit, you know? But we're going to plug in S, the length of that loop, right? Just so we're all, you know, on the same page. And so that's equal to mu naught I enclosed. Okay. And, well, if earlier we defined n as the total number of turns, right, we don't have to do this n over L because we're doing the entire toroid, right? I mean, up here, if we had the, you know, exact length of our solenoid and we wanted to make our Amperian loop fill the whole thing, then I enclosed is just I times the total number of turns. Where'd we go? Here, we do have the total number of turns in here. And so we can say I enclosed is the current, right, that's just going through the wire, right, but it's going through each turn, and then times n, the number of turns. And so if we put this all together, b times 2 pi r is equal to, well, mu naught I n. Then we can say for an ideal toroid, b is going to be mu naught I n over 2 pi r. Okay. And so there we have it. You know, so hopefully while I was doing this, you were able to kind of knock out the worksheet parts that have that filled out. And then the next section is modeling a current carrying wire as a magnetic dipole. Right. I don't think we need to go through the whole derivation. And so let's see, what do we want to do? And so this is if you have, well, let's keep our kind of color scheme going. So if you have a loop of wire with some current going around it, right, we had discussed that you can treat that like a magnet, right? I guess maybe I'll draw a magnet for that. North, south, and then we have magnetic fields coming out and around. And you know, there's more of them, and then you got the ones that kind of come out and go in. All right. And so I think what we're going to take a look at is if we were to go some distance perpendicular to that central axis, P, you end up with a magnetic field B of Z is equal to mu naught I. Right, this loop has some width R, so mu naught I R squared over 2 times R squared plus Z squared to the 3/2. And so the derivation's in the book, but I think this will do us just fine to just kind of state this result. And if you're interested, feel free to look through it. Cool. Well, we'll end it there for today.